Hello, everyone. Welcome to our global webinar series brought to you by Rockflow Dynamics. My name is Jessica Kalin from the RFD Calgary office, and with me today is reservoir engineer Eddie Evans from our Houston office. We would like to thank each and every one of you for joining us today. We are honored that you are able to give us 30 minutes of your time for this webinar. Our RFD team is working around the clock to maintain and increase support for our clients during these times from working from home. Despite the global changes, we continue to be there for you 24/7. During today's webinar session, all of our attendees' microphones have been automatically muted. Should you have any questions during this presentation, please go to the questions pane on the right-hand side of your control panel, as we'll be addressing as many questions as we can at the end of this presentation. Additionally, no need to take notes. This webinar is being recorded and will be uploaded to our RFD Europe YouTube page. Should you be left with any questions at the end, or if you have a suggestion for a future topic, please feel free to email us at asktnav@rfdyn.com. Each webinar in this global webinar series covers a breadth of topics, from geomechanics to cloud computing to hydraulic fracture and well placement optimization. The complete list can be found here. It can also be found on our YouTube page, as well as on the main GoToWebinar registration page where you signed up for this webinar series. Each of our webinars touch upon a different aspect within the integrated reservoir modeling process available in tNavigator. If you're interested in learning more about tNavigator or want to get started with a free trial, again, please don't hesitate to email us at asktnav@rfdyn.com. Now for today, we're live from Houston, Texas, and I would like to introduce you to reservoir engineer Eddie Evans.
Hi everyone, my name is Eddie Evans and I'll be showcasing the hydraulic fracture simulation uncertainty webinar. This is going to be a relatively short webinar, so we'll cover some of the more basic uncertainties and the ones that the most common that are seen when we do these uncertainty studies for hydraulic fractures. So to begin with, let's go over a really brief overview of our agenda. We'll go through a short introduction of what tNav is, how it works, and what it does. We're going to discuss hydraulic fracture in tNav to say how you make hydraulic fractures, what your options are, the advantages and disadvantages of each one. We'll go through the uncertainties to be covered in the software demo. Then we'll see a software demo in video form, and we'll end up with some Q&A sessions. Okay, so let's go to the next one. So the first thing to know is that tNavigator is a fully integrated solution. This large scope of functionality covers anywhere from geomodeling to PVT to SCAL, basic RE things, optimization, wellbore modeling, and flow assurance, geophysics. So it's a fully integrated package that allows for very deep and rigorous analysis and processing of the input data, in addition to the simulator itself. The big advantage of this integration is that you can leverage your entire asset team's expertise in a way that you don't lose a lot of data. Your tail end of knowledge that gets used to build a model doesn't disappear because you export it out of one software into another. So it allows you to leverage everyone's expertise and also collaboration to make a more robust study of what you're trying to achieve. So hydraulic fracturing in tNav, we have basically, the first thing to cover is that we have two ways of modeling hydraulic fractures in tNav. We have virtual connections and LGRs. So virtual connections, in essence, what you do is that you give it a fracture geometry, and from that fracture geometry, it builds connections to the global cells that fracture communicates with. The second one is LGRs, and these LGRs can have different options. So you can have uniform LGRs, logarithmic LGRs, and unstructured gridding LGRs. And the biggest advantage of unstructured gridding, which is unique to tNav, is that it can model complex fracture geometry through fracture templates and fracture point sets. That means you can actually digitize a complex fracture geometry that branches out or has multiple kinks and curves along it, and you can actually use that to create your fracture template. And that can then model a complex fracture geometry. You can add uncertainty to it. You can stretch it out, change the perm, whatever you want. You can also do complex geometry through point sets and through other format data that gets loaded into tNav Model Designer, And from there, it'll build an unstructured grid around that complex geometry. All right, the fourth thing to know is for simpler and bi-wing fractures, you can actually work with fracture tables. And this means you can do 700 fractures or hundreds of fractures at a time, and you can define a bi-wing fracture geometry. And you can build entire pad level wells relatively quickly and efficiently with a fracture table. And finally, we also have fracture arithmetics. And this allows for property changes in interpolation within the fracture cell or within the SRV. That means you can change things like perm, porosity, the saturation functions, the rock function numbers, all these things can be changed through fracture arithmetic. And it also supports the actual arithmetic keywords in which you can use a conditional statement to change a property in the schedule dynamically. So what are the tNav advantages? The first one is, like we mentioned, complex fracture geometry. Unstructured LGRs allow you to have this very complex geometry without necessarily having to create thousands or millions of additional cells. The unstructured LGR will go out and like subdivide the global grid only in the areas where your fractures themselves are. So you don't need to, so if a fracture hits a corner of a global cell, it doesn't need to subdivide the entire cell. It'll only subdivide that corner. Independence, wells, and fractures. So fractures, wells, and grid are independent of each other, which means that you can actually just cobble these together and flip the grids if that's an uncertainty. It also means that wells and fractures are not grid dependent, so they don't need to be gridded. Now, this is one of the biggest advantages of tNav. Before, what you needed to do to get a lot of this uncertainty done was you needed to flatten your well out so it's completely horizontal, and then you would need to go back and make sure that your fracture axis aligns with one of the main axes of the grid. So basically, you'd have a twisted situation in which your fractures and your grid would be in the same alignment, so you can actually create these logarithmic LGRs or even Tartan LGRs. The third advantage is fracture tables and templates. Like I said, both of these allow you to create large number of cases quickly and idealizations quickly, and it allows you to add uncertainty to these idealizations. Arithmetics, like I mentioned before, arithmetics can be used to change properties in the fracture and in this RV, and these can be based upon the fracture geometry, which is the fracture arithmetic, or based upon a conditional statement. So for example, if you have a threshold pressure at which you would want the property of a property to change, like a fracture pressure, you want to change the perm to a certain value, you can say, you can have an arithmetic keyword that basically says, if pressure hits threshold, then perm becomes a new value. And we also leverage this. All this is enhanced by the fact that we have high performance computing in tNav, which means that it's very good to make large number of parallel cases to run millions and millions of cells, which gives you the ability to run pad and field level simulations with hundreds of fractures and LGRs. Okay, so let's talk about the uncertainties to be covered in this short webinar. We're going to go through fracture geometry, things like half length, height, SRV, how big the SRV should be around your fracture. All this can be done in Model Designer, and the video will kind of start off how to create, not how to create the base case, but how to create the uncertainty from there. Fracture spacing, we'll go through fracture spacing as well. Basically, the cluster spacing, how close or how far apart fractures can occur. Fracture properties, how to change perm, how to change things like perm, how to change the saturation number and rock compaction number so that they switch between rock compaction functions or saturation functions, and also well spacing, basically how I can shift my wells closer or farther apart so that I can create the spacing study. Okay, so now we'll go ahead and look at the video demo and how to make this an uncertainty study, right? So what's really neat in tNav and Model Designer is that we have a workflow editor that works the same way as you would have a Python script. So it actually works a lot better than a Python script because we have built-in commands and we're also Python compatible. So right now we can divide our our uncertainty study basically between 4 parts. We want to do fracture geometry, fracture spacing, fracture properties, and well spacing, right? So let's do the fracture geometry. Well, the cool thing is that both fracture geometry and cluster spacing, you can vary both of those directions in the fracture table. So I'm going to add a fracture table. I'm going to say, well, I want to adjust the fracture table. So I'm going to add this fracture table here. And I'm going to say, okay, get values from table. And now, as you can see, the table has populated with all the things. Well, let's first do the fracture geometry. So we want to change the geometry. We want to change the half length and the height and the SRV. So let's do that. So let's do this. First variable, we're going to do half length. The half length starts at 75. Well, we have to make the maximum. The maximum value is going to be 100 meters or 300 feet. Minimum value is going to be 50 meters or 150 feet. 75, 50. Okay. Now we can come here and say, okay, half length, XF, 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 right? Now I'm varying half length. The next one I can vary, I'm going to vary fracture height, so I'm going to call it HF. And the maximum is going to be 40. The base is going to be 20. And the minimum is going to be 10. Right? So I'm going to come from input variables to your adjust fracture table. I'm going to scroll over to the right to select them into columns so you don't have too many. And I'm going to say, okay, HF, or I can also just type HF like that, right? HF, HF, HF. Right, so that's HF. So now we want to do the SRV size. So I'm going to do SRV. The maximum is going to be 30 feet. The minimum, the base value is going to be 20 feet, and the minimum is going to be 10 feet. So once again, I'm going to come over here and say SRV or SRV, 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 SRV. Okay, so that covers the SRV, right? So that covers geometry, right? We have fracture height, fracture half length. Everything is geometry till now. The next thing to do now is cluster spacing. Now this one's really neat because I'm going to call this spacing for cluster spacing. My start value, I'm going to say, okay, there's going to be 15 clusters per stage. Maximum, minimum, there's going to be 5. And okay, base value, there's going to be 10 because we have 10 right now. And minimum value is going to be 5, right? So I'm going to call that spacing. I can come over here and say, okay, number of fractures, spacing, spacing, spacing. And that covers fracture spacing. So right there, we've already covered 2 out of the 4. We've done fracture geometry and cluster spacing as uncertainties. The next thing to do is fracture properties. Now, we use fracture, to change the fracture properties, we use the fracture arithmetic. So I can actually come here and say adjust fracture arithmetic. And I can, in this case, I can fracture arithmetic, for example, to highlight it. And here is adjust fracture arithmetic. I incorporate that as step 2. I say get values from arithmetic. In this case, I only have 1. But if I have different ones, I had to drop down. So there we go. So let's do the next uncertainty. We're going to say fracture perm. So I'm going to do KF. Maximum value is going to be 750 millidarcies. Base value is 500 as it is now. And min value, I'm going to make 250, for example. Right? So I'm going to say, okay, KF, KF, KF. Right? Okay, so that's fracture perm. Let's say I also want to vary this fracture for the perm for the SRV. So I'm going to do KSRV. And the KSRV is going to be from 1 to 1 to 10. Yeah, basically unchanged. So I'm going to do KSRV, or you know, like we did before, you do KSRV, 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 KSRV. All right. Now we're not going to change rock num or sat num because those are not uncertainties. But we will vary the endpoints on the rel perm, and the we can also vary the amount of compressibility. So let's do the first one. Let's do rel perms. So we go on adjust analytical relative permeability table, right? So I'm going to add that. Come over here and say get values from table, and I'm only interested in changing the fracture table. And we're going to keep this simple. We're going to create a variable for critical water. So I'm going to create SWCR. I'm going to go from 0, and up to 0.25, right? So maybe 0.15. It's better, so it's not too big. So same thing. I come and say, okay, I want to SWCR, and that is now a variable. So that covers and you can do that variable for any of these inputs to the Cori correlation. Right, so if you don't think it's exactly straight line rel perms, you can come in here and make your Cori exponent for the oil water curve not 1, but go between 1 and 3, and maybe that helps you better. So that covers the Cori exponent. Let's also do the rock compressibility now. Adjust rock compressibility, and I'm gonna say fracture. Restore table, and I'm going to make this a variable. So I'm going to say input variables, rock comp, and this was, I'm going to go from value 1.5 e to the minus 5. Minimum is going to be 1.4 e to the minus 5, and maximum is going to be, let's make this 1.0 e to the minus 5, and this will be 2.5 e, 2 e to the minus 5, to make it easy and press it. Okay. So that's rock compressibility. I come in here, rock comp, and there you go. Now that rock compressibility is an input variable. So that covers fracture properties, right? We've changed the perms, we've changed the SRV perms, we've changed the critical water, we've changed the rock compressibility inside the fracture area. Now, what else can we do? Well, the last thing we need to look at as an uncertainty is well spacing. So for well spacing, I'm gonna go in here and shift my wells, and I'll show you how that is. So I go to translate, and instructional modeling, there's wells, translate well trajectories, right? So this would be the step. Now notice that there's a well filter. You may have to create a well filter. In case I've already created one, but I'll show you how to create one right now. So I need a well filter to just target my change only to one well at a time. So I'm going to close this webinar workflow. I'm going to come in here to the well filters button, and I'm going to show you how I created it. So you press the plus button, well filter 1, or in this case well 1, and in well 1 you click on the pencil button, and you basically say, let me see, remove all. I'm going to say, okay, well 1, add to filter, well 1. Right, and you basically do the same thing. Well 3, it used to be here. I click active filter, well 3. Right, so if you go back to the workflow, once you've created the filters, I can say, okay, well filter, this only applies to well 1. I'm going to shift, so I'm going to call this spacing 1 for well 1. And I want to shift my well 1, which is this well, and I want to shift it along towards well 2, which, if you can see at this bottom status line, it says from well 1, which is this one, to the right is positive x, right? So positive x. So I want to say, okay, well 1 can go from 0 feet, so basically it stays where it is. The minimum value is 0, so it's not going to go further away for now, and the maximum value is going to be 50. I can always make this negative 50, but then I have to do a couple other things to make it go left concurrently with the other one. So that's well 1. So I'm going to come in here, 0, spacing 1, shift along the x. I can add this rule again to translate well 3. right? And same thing, I'm going to call this spacing 2. In this case, it's going to be the opposite because I need to move it closer to the well 2. So I'm going to 0, negative 50, 0, and spacing 2, right? Now the last step to do it, we'd have to go in and say export case or export model, and I add that rule, and now this export model, I can press close, right? Or I can press test. Everything seems to run fine. Okay, so now that I'm here, what do I do? Well, now I can actually create an AHM case. I have a workflow, which is this one, that has steps, that has variables that need to be changed to create the case, right? So now what I can do is I can actually go to this little wand button, say create AHM project, and call this webinar. And I can press OK. I can even launch directly from here, but for now I want to press OK. Yes. It creates the thing. So for now, so I can show you the results, I want to say write wells. I'm going to say write all results. That means 3D results and everything, so I can showcase the final results. I'm going to do a simple tornado for now so we can see the effects of min and max for each one. And I'm also going to change one quick thing in the options. For new job options, I'm going to tell it to use my GPU because the difference between no GPU and GPU in cases like these LGR cases, are an acceleration of like between 30 and 80% of simulation runtime. So I'm going to press OK, and then I'm going to press OK. And basically at this point, what happens is that we have the tornado plot algorithm is going to start launching cases on its own. Okay, so let's take a look at the results that we have from our tornado launch. So let's first take a look at the analysis tab. So under the results panel, I can click on analysis tab, tornado, and then I can see which one affects the, for example, oil total the most. It looks like the one that affects oil total the most is spacing in a positive faction. So this is number of clusters. So the fewer number of clusters, the negative. There's the deviation at a negative value versus positive value, SRV, So that's what we have right now. But let's take a look at how the results actually look. So I can click onto the table tab. In the table tab, I have XF for half length. So case 0, which is the base case, has a half length of 75 meters. And case 1 and 2 are 50 and 100. So I can right click and say view results to view the results. In this case, I've already pulled them up in the background. And we can see how we have there's just the 001, which is 50 meters, and you can see that it's really short. And this is the 100 meter one, which is really long. So you could go to 150, and if I were to go to 150, these would intersect, and these fractures would actually interact with each other. So that's how we could do a very good like half-length spacing study based upon half-lengths. But we'll also the next one we'll look around for the actual well spacing. It's the next ones I'm going to show you. All right, so let's take a look at cluster spacing. Since all of these are basically the basic geometry that we already saw is sort of working, the next one I want to do is we want to do spacing. So I'm going to come over here, look for the spacing one, and spacing this is cluster spacing, which are cases 7 and 8. So I'm going to right click and say view results, and I have 7 and 8 already up. And as you remember, for cluster spacing we had 5 clusters in the stage, and for the low and for the high we had 15. So you can see here's 1, 2, 3, 4, 5, and you can see clearly here it's a very high density, and that's 15 clusters, right? Okay. So for the last thing we're going to view the results for the last spacing 1 and spacing 2. Now if you remember, we were treating each well as with an independent spacing type function, but you could change the spacing type functions as much as you want. So this one's just to show you can shift some wells to the right and some wells to the left. So what I'm going to do is I'm going to write the same thing. I come in here to table, I figure out spacing 1 and spacing 2. These are the 2 maximums, and since the minimums are 0, it doesn't really matter. So we can take 50 to the right, and 50. Well 1 is going to go 50 feet to the right, and well 3 is going to go 50 feet to the left. And if we right click, we say view results, we can view the results. And this is a case for well 1 right here. Goes 50 feet to the right, and as you can see, it moves closer. And there's this base, and the original one that you can see here, is where well 1 originally was. There was about this amount of space, about 2 global cells. There's now no space, and between well 3 and well 2, it's shifted, as you can see. That's just to showcase how you can shift the wells. You can make a function of from this well offset 100 feet, 100 feet, 100 feet to the right or to the left, depending on your point of origin. So see, and this is what's really neat. Because of this unstructured LGRs, you can actually get another fracture cell in the same global grid running parallel to the other fracture cells. And we were to stretch these out a bit more. Okay, so that's the end of the video. And basically, in summary, oopsie daisy. Oh. So basically, in summary, what we have is we have three different levels of things that we can say. AHM, we can leverage AHM lets us leverage both the simulator and model designer to create these very rigorous, very highly detailed studies with large amounts of uncertainty. Model designer allows us to create these cases quickly and have a base case. The one thing I didn't showcase in the video that's really interesting is if this were a history match instead of an uncertainty study, the best case, I could right click on the best case and I can say send variables back to workflow in model designer, which means that once that happens in model designer, where I defined all those variables, the start value gets replaced by the best case, and I can hit run on that workflow, and it'll essentially spit out the best case, and now that can be your starting case for a forecast or for whatever you want to do in the future within model designer. That also allows you to have very complex fracture geometry, very complex different regions within model designer, so it's very flexible in that sense. It's a lot more flexible than doing it in a deck for things that involve geometry versus just simple changes based on IJK indexing. Finally, the biggest thing that's the most important for us is that tNavigator, the simulator, it's fast simulation speed. It leverages GPU, CPU, and the unique unstructured LGRs. Allow for these really rigorous studies that allows for a lot of detail, allows you to actually not compromise your model and simplify it so you can run it. It actually lets you have the complexity that you need before you start simplifying the model. You can see can you run the complex model before you have to start doing all the things that we currently do, which is flattening out wells and aligning fractures, wells, and grids all together so that they're orthogonal to each other. So that kind of wraps up the webinar. Did we have any questions out there? Let's see. Give me a second to see if there's any questions. Okay, so I got 2 questions. The first one is, can tNav fracture tables be used to create a fracture for the injection period and for the production period? The answer is yes. What you would do is, as you saw, we had 3 lines representing the different stages. You can have as many lines as you want, and you can just, part of the things you can activate in those tables is saying, okay, I want to change the injection fracture is open from one date to this day, and then you have another line saying the production fracture opens from this date to this date. So you can simulate injection and production, and that is really good for flowback. So we've done a lot of history matching with flowback that way. Can properties in the fracture LGRs be changed based on a conditional statement, like a threshold pressure? So I kind of went over that in the PowerPoint already, but yes, it's possible. You can use the arithmetic keyword to change properties based upon some conditional statements. It can be a threshold pressure, it could be like a transmissibility multiplier, it can be a saturation, it can even be an IJK indexing itself if you're interested, or a cell size as well. I think that's all the time we have available for today, so thank you very much.
Thank you very much, Eddie, and thank you everyone for listening today. If you wanted to go back to watch this recording, it will be uploaded on the RFD Europe YouTube page. as well as all of our previous sessions. If you go to YouTube and search RFD Europe, you will be able to find all of our past webinar sessions up there on YouTube. Our next session will be on Tuesday at 800 hours UTC, and the topic will be characterizing your model using FACES modeling. I'm going to leave that questions open just for a couple minutes more. If there was something that you just thought of that you wanted to ask us, please feel free to type it in the questions and we'll email you the response in the next couple days. Thank you very much, everyone, and stay safe.